Welcome back, digital detectives, to the history of cryptography, Behind the Code, Episode 5, your go-to series that lays out the history of cryptography, where we've been, where we are, and where we're headed. Over the courses of Episode 1 through 4, we navigated the complex landscape of cryptographic ciphers, unraveling intricacies and potential vulnerabilities. Our journey has laid the groundwork for us moving forward, beginning with the origins of cryptographic ciphers. We now shift our focus to the world of DSAs, or digital signature algorithms, the modern-day equivalent of a digital courier, which signs transactions and proves identities within a storm of chaos on the internet. So let's ponder the origins of digital signature algorithms. Cast your mind back now into the dawn of the internet era, a nascent, developing technology platform for communication, business, the exchange of ideas. However, this newfound connectivity brought with it significant risks, particularly concerning the trustworthiness of digital documents and transactions. How could one verify that a person on one end of the transaction was actually who they claim to be? The solution emerged in the form of DSAs, a mathematical masterstroke in engineering designed to solve this very problem. DSAs fulfill two essential roles. One, they confirm the authenticity of a message or a document, guaranteeing it originated from the stated sender. After confirming the sender, it verifies the integrity of the contents, ensuring that they remained unaltered during transmission, similar to the modern equivalent of ancient wax seals, but digital. You might be wondering, how do these DSAs actually function? So let's demystify this. A typical DSA is a set of two keys, a private key and a public key, together known as an asymmetric key pair. The private key is created first. The public key is a derivative of the private key created second. They are mathematically linked together. The private key is a closely guarded, essential secret acting as the keys to the safe, whereas the public key is freely distributed, like the address for your mailbox. Digital signatures are used in secure email transmissions, document signing, online banking and transactions, identity verification, and finally, yes, blockchain. For the rest of this video, we're going to focus on the blockchain use case, starting with Bitcoin. In Bitcoin transactions, when you initiate a transaction output, you're essentially signing this transaction with your private key at your terminal and submitting your public key along with the transaction to a node for verification. The receiver is able to then verify the sender by comparing the transaction with the public key. In Bitcoin, this fingerprint, along with the transaction details, is broadcast to the entire network. A node receives a transaction and it broadcasts it to all nodes that it's currently connected to. In the next and final episode, we'll walk through this process in a lot more detail. What's truly elegant about this mechanism is its blend of simplicity and robust security. From a classical perspective, your private key is the only tool capable of generating a signature that your public key could be used to authenticate. A private key can only produce a public key, not the other way around. This is also known as a one-way function. So this dual key system effectively safeguards the sender's identity and the message's integrity, forming a secure and streamlined process. Or does it? A little more on this later. So mathematically, how do these DSAs work? Well, factorization plays the key role, particularly in algorithms like RSA, which is widely used in DSAs. The security of RSA is deeply rooted in the difficulty of factorizing large numbers, also known as a modulus, which specifically the product of two large prime numbers when multiplied together. This mathematical challenge forms the backbone of RSA's encryption and decryption process. When a message is signed using RSA, for example, the sender's private key is used to create the signature for the transaction. For verification, the receiver uses the public key. The public key, linked to the private key through mathematical factorization, validates the signature's authenticity. The complexity of factorization of such large numbers ensures that it's classically, computationally infeasible for an unauthorized party to reverse engineer the private key from the public key, thereby maintaining the security integrity of the digital signature and message. This reliance on factorization underscores the intertwining of advanced mathematics and cryptographic security, making DSAs not only a technological feat, but also a testament to the power of mathematical principles in securing digital communications. This difficulty in factorization large prime numbers is perhaps the most important component of what secures the Bitcoin network. The emergence of quantum computing presents both fascinating opportunities, formidable challenges, particularly in the context of banking, web transactions, governmental communication, but also Bitcoin and nearly every other cryptocurrency. One notable development in this area is Shor's algorithm, developed in theory in 1994, which could be capable of the factorization problem on a sufficiently powerful quantum computer, which is the cornerstone of many cryptographic systems, as we've discussed, including those used with Bitcoin. Shor's algorithm, theoretical at the time, but when coupled with a sufficiently powerful quantum computer, poses a significant threat. This is because it could potentially break the elliptical curve cryptographic schemes that secure Bitcoin wallets and transactions. The prospect of quantum computers being able to utilize Shor's algorithm to decipher these cryptographic puzzles at unprecedented speeds brings us to a critical juncture. It underscores the need for us to maintain the evolution of our cryptographic practices, continuing to pave the way for the development of quantum-resistant algorithms to safeguard digital assets like Bitcoin against the advancement of quantum computing. This looming quantum failure is not just a challenge, but also an invitation for innovation, steering the world of cryptography into uncharted waters. So, what would these attack vectors look like to Bitcoin? How could they be executed? Stay tuned for our next episode where we'll break this down into simple terms and go over exactly what that threat could look like.